Hi everyone, my name is Matthew. I'm a postdoc at the University of Michigan, and in this short presentation I'll be overviewing recent work on phylogeny-based methods for detecting multilevel selection. A major motivation in this work is to support research in open-ended evolution related to evolutionary transitions and individuality. These are events where existing replicating entities within a system combine to create a new composite organism. These type of events have occurred numerous times in nature, notably in the evolution of multicellularity and the evolution of eusociality among insects. Evolutionary transitions often involve cooperation among lower-level units in service of the success of the collective. In many contexts, however, individual low-level participants can gain a short-term evolutionary advantage by reverting to selfish behaviors. However, such lineages are typically short-lived as the higher-level collective is harmed. An example of this phenomenon being cancerous growth within multicellular organisms. These sorts of trade-offs between selection contexts are referred to as multilevel selection, and they're characteristic of evolutionary transitions. Given the diversity of computational model systems used to study open-ended evolution, a key challenge exists in developing generalizable methods to detect and quantify signatures of such multilevel selection dynamics across systems. Multilevel selection can arise in additional evolutionary scenarios beyond transitions in individuality, another example being epidemiological contexts. In these contexts, different selective pressures can exist for the behavior of pathogen in proliferating within a host versus its behavior in transmitting between hosts. Trade-offs can arise, for example, where some traits might be favored for growth within the host but ultimately reduce the viability of the pathogen in transmitting between hosts. For example, very rapid proliferation within a host can increase the disease burden to an extent that the host dies and becomes a dead end for the pathogen. In epidemiological context, detecting multilevel selection dynamics can be useful in understanding the evolutionary forces at play on a pathogen and potentially forecasting future evolutionary trajectories. To achieve a quantitative screen for multilevel selection dynamics that generalizes across a variety of model systems, we turn to phylogeny data. Given the fundamental nature of hereditary relationships in evolutionary systems, such ancestry data is broadly available and generally comparable across different model systems. In particular, we focus on an approach to screening phylogeny data proposed in recent work by bioinformaticians Franceschi and Volz, focusing on the suitability of these methods for work with artificial life models. Given the capability of simulation systems to generate data under conditions explicitly configured either to include or exclude multilevel selection dynamics, we sought to explicitly test the accuracy and sensitivity of these phylogeny-based screening approaches and to extend these methods as necessary to improve their accuracy and sensitivity. But to start off, let's talk a little bit in general about how we would expect the signatures of multilevel selection to manifest within a phylogeny. Fundamentally, in screening for multilevel selection, we'll be looking for particular characteristics involving individual mutations exhibiting multilevel trade-offs. Specifically, for individual mutations, we'll be looking at the frequency at which the mutation arises or is observed, and the subsequent evolutionary success of clades containing that mutation, as measured by duration and size. Of course, we have very intuitive expectations for the behavior of mutations not under multilevel selection. We expect harmful mutations to arise occasionally through random mutation, but ultimately have short-lived clades as they get selected out of the population. Neutral mutations under drift processes will have more stochastic variability in the evolutionary outcomes of their clades, and of course, beneficial mutations are expected to more frequently grow large, long-lived clades compared to neutral or deleterious mutations. In the case of mutations under multilevel selection trade-offs, we expect rapid short-term growth, but ultimately short clade durations. So if we sample these mutations from the population, we'll see them more often than neutral mutations due to short-term selection, but the longer-term outcomes of these clades will be curtailed. If we switch from molar plots to looking at a phylogeny, what we'll be looking for here is a particular mutation that might have arisen independently multiple times. We'll label the tips of our phylogeny that have the mutation here with red dots, trace back up the phylogeny to estimate the origin of each instance of the mutation, and then perform our statistics on the mutation-sharing clades that descend from these points. After some normalization, we can ask whether these clades are arising more often than expected by chance, and whether their duration and size is more curtailed than we'd expect under a neutral hypothesis. Getting briefly into the weeds, a really important aspect of this methodology is normalizing clade sizes and durations to neutral expectations. Working with high resolution, densely sampled phylogeny data characteristic of in silico ALife models, we found that normalizing against the sister clade to which a mutation arises gives lower quality results compared to normalizing to a larger set of mutational clades arising from other mutations within the dataset. And so we adjusted the originally proposed normalization scheme to get better results with ALife data. To test the accuracy and sensitivity under the model under challenging conditions, we generated test datasets using an agent-based epidemiological model of COVID-19. These synthetic datasets comprised phylogenies of about 1 million tips, and we ran screens for multi-level selection effects of different magnitudes, ranging from small to large effect sizes. We found the method to reliably detect mutations with large multi-level selection effects, but found limited sensitivity for mutations with smaller effects. For instance, we were able to only detect medium-sized 30% effects in 2 out of 5 trials, and we were unable to detect 10% effect sizes. Given these results, a question we're interested in exploring next is how the sensitivity of these screening methods scales with the magnitude of the underlying phylogeny dataset. If you're interested in more details, the QR code links to the full paper, and of course, I'm happy to have any discussions one-on-one. I'll wrap up by thanking my collaborators and our institutional support, and I look forward to further discussion.